Lecture number 15, Organization of Digital Modulation. We have basically baseband modulation and the passband modulation. In the both case we have the binary modulation and the M-ary modulation. Most of the cases of baseband binary modulation is discussed in the last 14 lecture, and now we will see this classification very briefly again in some other senses. So you can classify the baseband binary modulation in two types. One is called antibodal signaling, another is called orthogonal signaling. Antibodal signal is analogous to the polar signaling, which gives basically negative correlation, and orthogonal signaling is like on-off keying, and which gives the zero correlation. The negative correlation is one of the advantage over zero correlation. It reduces the probability of error. So this is the signal representation of the binary baseband antibodal signaling, and here is the signal space diagram. You must remember that this antibodal signaling gives negative correlation. Now baseband binary orthogonal signaling. To satisfy the orthogonality property, the signal S1t and S0t has to be satisfied this equation. So it gives us the correlation is 0. You can represent the modulated signal by this equation. Very simple. Now the example of baseband orthogonal signaling. So on-off keying is a baseband orthogonal signaling. Here is a typical example: S1t and S0t. This two signal this constitute the orthogonal signaling baseband binary. So this is the way to represent the data in this particular signaling scheme. Now passband signal, this sinusoidal signal is another example of orthogonal signaling, but this is basically in the passband case. We will see in details in the passband signaling. Just note that these two signals S1t and S0t are orthogonal to each other if and only if the both F0 and F1 are the integer multiple of 1 by 2t, where t is the sampling period and the data is defined by 1 by t. That is RB. So this is F0t and this is F1t. Here M0 and M1 are the integer multiple. So this is the expression if you take the difference between two signal, and note here that M1 cannot be equals to M0. If M1 equals to M0, then you cannot distinguish F0 and F1. In that case both are same. So the minimum difference between them is 1. If M1 minus M0 is 1, then we called this is as MSK, minimum shift keying. In that case, this particular frequency difference between two orthogonal signals become 1 by 2t, that is RB by 2, because 1 by t is RB. So here is the proof why you need the two signals frequency have to be integer multiple of 1 by 2t. You can see it from here. Now lecture number 16. In this lecture we will discuss the baseband M-ary modulation. So in this case basically we have orthogonal modulation, orthogonal signaling, simplex family, and the biorthogonal family. Details description of biorthogonal family is not discussed here, and for the orthogonal signaling we have the zero correlation similar to binary modulation, baseband binary modulation, and for simplex signaling it gives the negative correlation like antibodal signaling in binary baseband modulation. So M-ary baseband orthogonal signaling, you have a set of capital M number of signal waveform, where M is defined as 2 to the power k, where k is the integer. It is known as the word length, and you consider the energy of each signal is EP, constant EP. So they are orthogonal to each other, so the correlation is 0. So here is one example of M-ary baseband orthogonal waveform. So this is called 4-array pulse position modulation. They are orthogonal to each other, and the value of M here is 4. So the k word length is 2. So you can represent S0t as 0 0, S1t 0 1, S2t 1 0, and S3t is 1 1. So these are the mapping. So here is another example of M-ary baseband orthogonal signaling waveform. This is called code shift keying, 4-array CSK, code shift keying. All 4 signals are orthogonal to each other. We know EP is the energy of each signal SMT, but one of the important property is the energy per bit EB. It is EP by K, which is known as energy per bit. This is a very important parameter for digital signaling scheme. In this case, K is defined as log M with base 2. Now M array baseband simplex signaling. In this case, this is similar to the antibodal signaling in the binary baseband modulation, right? And this simplex family can be obtained from the orthogonal family from this relationship, right? And this is the energy equation of the simplex family, and you can see that this energy of the simplex family is smaller than the energy of the orthogonal family in the baseband M array signaling scheme. So simplex family contain very less energy, and they also give the negative correlation. They give the negative correlation. So you can say that this simplex family gives the same probability error, or it has been calculated that simplex family gives the same probability error as the orthogonal family with less energy, right? So simplex family is energy efficient. There is a long standing conjecture is that of all the M array pulse alphabets of a given energy E, there is no other alphabet which can give you the smaller probability of error than the simplex set. This is like the polar signaling is the more efficient signaling in terms of power, and similarly for the simplex set. And we have also seen that this simplex set is analogous to our antibodal or the polar signaling in the binary baseband modulation. Here we have seen this. This is analogous to antibodal or polar signaling. Now M array baseband bi-orthogonal family, you just take the m by 2 number of orthogonal pulse. After that, remaining m by 2 orthogonal pulse, take it is as a negative of this previous m by 2 orthogonal pulse. Then you got the family of bi-orthogonal family. Now in case of baseband modulation, if you increase the number of m, right, the bandwidth of the modulation scheme increases. So bandwidth grows with m in baseband modulation. So this creates a problem to deal with in the band limited channel. So the solution is that use Nyquist pulse. But it is not easy to construct orthogonal and the simplex or the bi-orthogonal family using the band limited Nyquist pulse. In the binary case it was very easy, but in case of M array case it is not very easy to produce the orthogonal signaling or simplex or bi-orthogonal using Nyquist pulse. In that case you can use the Nyquist pulse in M array ASK fashion or PAM fashion, pulse amplitude modulation fashion. So here is 4 array PAM or ASK. Here ASK means the amplitude shift keying, as the amplitude of the signal is varying, and this way you can convey the information in the band limited channel in case of baseband modulation. And this is the signals constellation diagram in real time for 2 array ASK and 8 array ASK. So far we have discussed about the baseband modulation. Thank you.